Okay, I guess you can hear me. Okay, thank you very much, first of all, to the organizers for inviting me to give this talk. It's a great privilege to be here, and I've very much enjoyed not just the setting, but the whole meeting and also the videos of 40 years ago. They tell us a lot of interesting things. How much have we actually learned since then? Are we any better since then? Certainly the questions were better back then, I think. They were a bit more aggressive. But I'm not trying to change the style now for my talk. So the topic of my talk is Magnetosphere-Ionosphere Connection at Saturn. We've heard about the general topic this morning and also yesterday. But my focus is going to be the atmospheric end of the story. So what happens to the atmosphere? The general top theme that it fits into is that of space weather, which of course is a popular theme on Earth. But more generally, more broadly speaking, I would say it's basically the question: how does energy propagate from the sun to the planets via the solar wind and via magnetospheres? There has been 10 years ago this study by René Pranget tracing a CME throughout the solar system from the sun to the Earth, to Jupiter, to Saturn. And so this is the kind of nice study which broadly motivates our work. More recently, there has been the Saturn Auroral Campaign, which follows a similar spirit. Measurements made in the solar wind at 1 AU, extrapolated with a model to 10 AU, and then compared with auroral observations or in situ observations by Cassini. So this is just the broad background. And first of all, what am I trying to say, and why am I trying to talk about that today? Basically, we know that, we've heard this week that Magnetosphere-Ionosphere coupling at Earth is a very mature discipline, thanks to efforts of many in this room over the past 50 years, and of others. At the same time, the giant planets have magnetospheres and ionospheres as well. But I would say that studying their coupling is still what you could call exploration science. We really don't know much about them yet. And if you want a summary of my talk, that's basically going to be the summary, so we can move to the next speaker. I will just explain how little we know and fill it in with some eye dust provided by models. But in the end, I think we're better at asking the right questions, but we're still looking for a lot of the answers. So what are some of the questions with giant planets? One key issue is that we don't understand the energy balance in the thermospheres of giant planets. Another one is that I don't think we understand the highly variable structure that we find in their ionospheres, and I will show examples of these two later. Another aspect is that Saturn's changing magnetosphere rotation rate is still a puzzle. Ginger provided a very nice answer to this problem, and the only thing is that we don't yet know if you impose such vortices in the atmosphere, what processes call the vortices in the atmospheres. So in a way, all of this is partly about magnetospheric physics, partly about atmospheric physics. And that makes it particularly challenging in many ways. I think scientifically, investigating the giant planets is very rewarding for both sides, for Earth and planetary scientists. Yes, you can learn about Earth as well by studying the planets. We look at the same physical processes under different boundary conditions, more extreme boundary conditions. And certainly, I started off in terrestrial atmospheric sciences, ionosphere, thermosphere physics, and moved on to the planets later. And I think I've learned a lot about Earth in retrospect from this. Okay, so the energy crisis, or the thermospheric energy problem, is nicely visualized by this problem. by this figure, it shows you thermospheric temperatures on Saturn, observed by the Cassini UVIS instrument, and also the green dots here by the Voyager UVS. And these are the UVIS have been recently analyzed by Tommy Koskinen and published last year. Also shown are observations of H3 plus temperatures in the polar ionosphere, which Henrik Melin published, only in the southern hemisphere so far. We kind of assume that the two are almost the same. One is at the base of the thermosphere, and this here is more at the top of the thermosphere. They're roughly isothermal. Our model suggests that the difference between them is in the order of 50 K. The bottom line, or the main message of this plot, is that there's an average temperature of about 400 to 450 K in the thermosphere. If you then take models such as ours, you get this embarrassing curve over here, this dashed curve, which I don't bother following down. It's basically, we drive our models at auroral latitudes with processes that I will just show in just a second. With Magnetosphere-Ionosphere coupling, we get the same temperatures as observed, but at low latitudes, we have no chance of matching the observed temperatures. In fact, we get about 200 K at low latitudes. And this has been a very annoying problem that has bugged us for many, many years, and it's still unresolved. And I'll get into that a bit later. So it raises the general question of what the energy and momentum drivers are in the upper atmospheres of the giant planets. We have, as candidates, solar or stellar radiation, stellar if you talk of exoplanets. You have magnetospheres as drivers of atmospheric circulation and energy. And then finally you have internal redistribution as well, from the interior to the outside via, for example, waves. And understanding the relative balance of these is really the crux of the whole thing. Just a quick figure of Saturn's ionosphere, and you will be able to tell you about that in great detail. These are radio occultation profiles of electron densities on Saturn, and you see it's a complete mess. In terms of variability, it's very interesting. I mean, the mess not in terms of the observations being a mess, but the ionosphere is highly variable from one profile to the next, and it's a puzzling trend. The red ones are low latitudes, the orange ones are high latitudes. As a terrestrial, you would say the subsolar point here, the subsolar point has the largest electron densities, but on Saturn it has to be the other way around, of course. So the higher densities are at high latitudes, and this does not include auroral latitudes, as far as I know. So understanding this has been quite an effort, and my colleague Luke Moore, he has spent some time on this as well. Possibly it's related to the influx of water from Enceladus and partly also from the rings. So this has become a more chemical problem. One thing I'm not showing here is there's a trend difference between dawn and dusk. Densities are higher at dusk than at dawn, and that makes perfect sense, that we understand, because on the night side there's recombination, so once you reach dawn, the temperatures, the electron densities are lower. Very briefly, this figure, which nobody wants to see anymore, Magnetosphere-Ionosphere coupling, how it works. My message is just that the departure from co-rotation in the magnetosphere leads to the extraction of angular momentum in the atmosphere, out of the atmosphere. That's why I'm concerned with it. It generates westward winds. We're looking down at the North Pole here, and the red contours mean westward zonal winds. And you see sort of this band at auroral latitudes of westward winds. This is essentially against the sense of rotation, so this is an extraction of angular momentum from the atmosphere. The effects in the atmosphere are twofold. On one hand, you have ion drag, the J cross B, and on the other hand, you have what we call Joule heating, and this is sort of the effect of the currents heating up the atmosphere, and also we also have included a response of the neutral winds in that. So how do we simulate these regimes? We are talking about magnetosphere versus atmosphere, and the two communicate via the magnetic field and via an electrical current, which is sort of electric field and energetic particles. All of these are the communicators between these two different regimes. Magnetosphere is obviously treated by MHD or hybrid models, and the atmosphere by collisional fluid models. So this is sort of my end, the blue end. But and this is an overview of the model we used. We call it the Saturn Thermosphere-Ionosphere model, or STIM. It's a series of 3 coupled models, and now Jinja has provided us with crucial and very useful input from the magnetosphere in terms of electric fields and the patterns where our peak electron flux is incident on the upper atmosphere. So this connection is really useful, and it's sort of a new era for this kind of modeling for us. I'm not going to go through all of this. Essentially, it's a model based on what terrestrial people are familiar with, the CTIM model of Tim Fowler-Rell, or the coupled thermosphere-ionosphere model of Earth. That's how it started its life, and we've since transferred it to Saturn and to other bodies as well. We have high latitude particle precipitation and ionization, and we self-consistently calculate the ionization rates of the energetic electrons through a particle code. And then we have the high latitude electric fields from the Batsaras model, and then a few other features which I'm not going to go into. And a generic ionosphere profile. This is sort of auroral, and the right side is equatorial. And you see sort of, this is a very steady state profile which has none of the variability seen in the observations, of course, but it does give you a reasonable background. It teaches us a bit about the relative abundance of ions, which so far haven't really been measured. H3+ is a major ion at low latitudes. At high latitudes, it's only in the bottom side ionosphere, and then overtaken by H+. With those boundary conditions, basically what we do this year is a local time plot in the auroral region. We have an incident electron flux in our model, which is time varying. It peaks just before dawn. Geographically, at the locations of the maximum downward field aligned currents, and this location is given to us by Jinja's model, and I will show you the patterns in just a second. Our model, the ionospheric code, then then goes through the ionospheric chemistry. This gives us ionization rates. Then ionospheric chemistry gives us conductivities. Here shown is the Peterson conductivity. We also calculate the Hall conductivity, of course. And then those ultimately lead to Joule heating, shown here as the blue line. So these are the kind of calculations that the model carries out, and they're all self-consistently treated. And the end result is then a temperature profile shown here, for example. This is from the southern pole to the equator. In the polar regions, 400 K-ish, and those are fully consistent with observations. But, and here's the problem, it drops off towards the equator. And a bit more about that in just a while. This end here, this temperature, we can control in the calculations by basically tuning these two parameters, these two free parameters, the energetic electron flux. We're assuming 10 keV electrons here. So this flux can go anywhere from 0 to 1 or more milliwatts per meter squared. And then we can also adjust the strength of the electric field. In this case, in this figure, this is from our 2012 paper, I'm letting it run from 80 to 100 millivolts per meter. And then you get, in response to these changes, you get changing temperatures in the auroral region. So you can basically try and match this best with boundary conditions from the magnetosphere to get and try and reproduce the atmospheric temperatures as well, and also the H3+ column emission. So this is our way of, in a way, constraining the model with observations. Now, talking about the energy business. This here shows you on the left the thermal heating rates by two processes, Joule heating and EUV heating. This is a cut from the South Pole to the equator. And here you see that the EUV heating is, so this is in millivolts per meter squared. It's about 0.04 milliwatts per meter squared. It's on the day side, compared with about 1 or 2 milliwatts per meter square of Joule heating. So this shows you how insignificant EUV heating is. As you move out in the solar system, the sun is less prominent than the effects of the magnetosphere. However, then our model also calculates the internal redistribution of this energy by winds. And here it's an interesting story. This line here, this colored line, is the adiabatic heating rate versus latitude again. And you see that the scale here is about a factor of 10 larger than here. So in other words, the energy deposited here at high latitudes also through the acceleration by the magnetosphere, this westward acceleration, anti-corrotation, drives a lot of dynamical energy redistribution. And really the whole energy balance is dominated by dynamics. So you have to be very careful if you use 1D thermal models only. You cannot leave out the dynamics. They're crucially important on these bodies to understand the energy. How am I doing with time?
You have 3.5 minutes.
Ouch. Okay. Oh my God. Okay. Right. So another story which terrestrials have gone through as well decades ago, the question of resolution of these models. This here just shows you lower or standard resolution that we used to use. And then if you switch with exactly the same inputs to a higher grid resolution in your model, you get dramatically different results. So you have to be careful about resolution. Here in the vertical winds, for example, you see with the higher resolution that we use now, a lot of interesting structure that was completely absent before. And the zonal wind change is dramatically different as well. So you have to be careful about resolution. That's more of a technical point, really. Okay, now I would like to just show a few results on variability in the auroral region, motivated by observations such as these, where you have sort of variation in auroral emissions, which are then matched by variations in auroral power by about a factor of 2 or 2.5 variation in power has been observed. So Jinja has kindly provided us with the inputs of the electric field for two different cases, normal solar wind pressure and high solar wind pressure. He showed this earlier. On the atmospheric side of things, this is just the total electric field in millivolts per meter. You see some differences between these two cases. The magnitude of the electric field is relatively low, so in the 20s of millivolts per meter. And this is, from the atmospheric perspective, a little bit too weak, because we to match the temperatures in the polar region, what I showed earlier, we need something in the order of 50, 60 millivolts per meter. So therefore, I've in the following multiplied these a little bit by a factor to beef them up a bit. And so I've defined two conditions, quiet and disturbed. Quiet gives you, we assume, an average electron flux of 10 kV electron flux of 1.6 milliwatts per meter squared, and a maximum electric field strength of 42. 1 minute, oof, that was fast. And disturbed, we beef this up by a factor of 2.5, and here by 1.5. So then we get sort of, this is just an idea to give you an idea of Peterson conductances, how they change in the atmosphere. Total electron content, quiet and disturbed. Just to show you also the difference in the pattern. Joule heating that results from that. Note the differences in scale here. In the disturbed conditions, it's a lot higher. And then the temperature response. So here, this shows you kind of the time delay. There's pulse, 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 pulse as a function of time. And I'm looking at different snapshots at different times. So what you see is an enhancement of temperature. This is now the temperature change, the difference, as a function of time. So at the end of this pulse, you have an increase of maybe 20 degrees Kelvin, which is nothing really. At the end of the second pulse, it's more. At the end of the third pulse, it's even more, and then even more. And this shows you the time lag in the atmosphere. It's an atmosphere with a high heat capacity, so you need a lot of time to heat it up. That's why the response in the thermosphere is very slow. And with the winds, it's a bit faster. I'm doing the same here, an animation. This shows you meridional winds and zonal winds. They respond more directly to the changes in forcing. Note, however, that these disturbances are much confined to the polar region. They don't really propagate much equatorward. This is different than on Earth. I'm almost done. This busy plot shows you the mass flux as a function of latitude, and it shows you very nicely sort of the contours are, the arrows are the meridional and vertical flux cells, and the contours are the zonal flux. But it shows you very nicely how the atmosphere is subdivided into cells as a function of latitude. So this, and just to show you an idea, this is the size of Earth in comparison to this. So the massive size of these atmospheres basically prevents communication of the polar region with the equatorial region. And this breakdown in communication as a result of sheer size is what really constrains the effects of magnetospheric storms to the polar regions. Finally, you can estimate thermal relaxation timescales from these studies, and they're about 200 hours here, so that's about 20 Saturn rotations. In fact, it's actually a bit more than that. So it takes tens of Saturn rotations to relax down in temperature. The wind dynamical timescale, it's much faster for the winds to relax down to previous values, although I'm running out of time, so I'm not going to go into that. The next steps, this is just showing you an example from Titan. The next step is really to include forcing from the lower boundary to take into account vertical coupling. This is how we did it on Titan. And on Saturn, it would look something like this. Zonal winds currently, and this is what we aim to do. This has been done on Earth. We're just doing it on Saturn. A summary. So we have this capability of simulating the response of Saturn's atmosphere to the changes in solar wind pressure. And I think the key to understanding, to solving many of the science puzzles is going to be to understand the winds and the circulation in the atmospheres. And I think we need to include now the forcing from the stratosphere to better understand that. I think the models allow us to understand the timescales involved in all of this and question the validity of steady-state assumptions. We have often used steady state, but I don't think steady state applies on the giant planets. And then finally, lessons learned from Saturn I think are useful for Jupiter as well, and also for exoplanets. And I'm going to take questions with this advertising thing as well. We have just published a book on Titan, which I hope everybody will get their libraries to buy so that we make lots of money out of it. And I'm sorry for overrunning.
Just because you skipped over it so fast at the end there, I just wanted to ask a little more about atmospheric forcing from below. It looks like it's very important at the low latitudes. Do we know enough about it to specify that? Okay.
This is from a GCM. Which one is it now? Fritzen, I think. Forgot now. This is from another model. There are very few constraints only. Observationally, there are some, but this is from another model. And basically, on Titan, I've done something similar. I've just taken the output from a different model. This is the lower boundary. This is from a different model of Titan, a climate model. I've taken that as my forcing. And the interesting thing is that the variability, all these wiggles and waves, and those are the ones that make it interesting. Because you can, this other picture is just a steady state input, and you get a steady state rotation of that's not very exciting. What you want are all these waves, and they're going to affect, when they dissipate, they will affect your momentum balance. And so that's where it gets interesting, and we want to do that.
I'll get that.
Excuse me.
Well, thanks for the talk. I was going to ask you a little bit more about your treatment of the superthermal electrons at the high latitudes at Saturn. I was wondering, you skipped over a little quickly, do you calculate the electric fields with the superthermal electrons, the parallel electric fields, self-consistently? And the reason I ask is at Earth, when you allow the superthermal electrons not just to play in terms of depositing energy and creating ionization, but you let them play in the creation of the parallel electric field, it changes the scale height pretty significantly.
Yeah, no, we don't. I mean, the model I use, shown here, it's the superthermal electron transport model by Galland. And we simply impose a flux. We say this is the flux, and what happens, what are the ionization rates in the atmosphere resulting from this flux of particles at this energy. I showed you 10 keV, but we have done it for other energies as well. We don't adjust then any parallel electric fields or otherwise. No, we don't.
It might be something to look into to see.
Sure. Thank you.